So, okay, in unit 2 here, we will have the test that cover chapter 3 about probability rule, and chapter 4, which we start talking about discrete distribution. So, in the practice test set here, we have about 21 problems, covers cover all the topics um, we discussed in chapter 3 and 4. So let me scroll down quickly. You can see the structure here. We have three basic probability rules. We have for one about the probability density functions of discrete random variable, and then for three we have binomial distribution. Okay, so let us look at each problem. So in the first problem about uh, basic of probability and terminology, state whether each of the following scenarios is likely, unlikely, and somewhere between. And remember that probability of zero is impossible and one is guaranteed to occur. So this is the most basic thing, right? We should know about probability. Uh, uh, how likely an event happen, right? Uh, likely, surely, right? Impossible, something in the middle, likely, unlikely, or maybe even chance, which is when in the case you have a probably half, right? So the first part of this problem is people with some college education stay married at least 20 years at a rate of 67%. So if this is the case, so the probability here we we have a 67%, right? The rate probability, right? So here we talk about uh, like the proportion, right? Probably a person get some college education, marry at least 20 years, for at least 20 years, stay married at least for 20 years, right? So, which means in this case, we on the high side, but not sure, right? We more than the even chance. So 67% here should be likely, right? Likely. Um, you have uh, at least one meal today. So in this case, you have at least one meal today. I think like for most of the people, right? Most people, right? It will kind of surely, right? Almost sure. Maybe for some people, it's not true, but most of people. So this probability must be kind of close to one, right? Close to one. Very likely, right? You have at least one meal. A woman has a baby and it's a girl. So this case, roughly speaking, we have a 50%, a half probability of girl, half probability of boy. So means in this case, it's just a even chance, equally likely. And then here, like, your best friend won the Mega Millions lottery. So to win the lottery, Mega Millions, it is something we consider very rare, very rare. Those probably pretty much like almost like zero. Okay. So basically, this is something very unlikely, right? Um, uh, uh, Pretty much we can say pretty much like almost impossible, right? Impossible. So that person must be extremely lucky to win the lottery. So this is very unlikely. So let us check the solution here. Somewhat likely, right? Which is more than 50%, uh, very likely, right? Close to 1, equal likely, 50%, and very unlikely, right? So this is the type problem where we need to be able to specify what's experiment, what is a trial, and what is the outcome. So let's look at part A first. A computer randomly generates number 1 through 100 for a lottery game. Every lottery ticket has 7 numbers on it. So if this is the case, so what happened in is that the computer, they will generate 7 number for the ticket, right? 7 numbers for the ticket. Um, and say let's assume like we have just one prize, right? Maybe the for the with the winning ticket. Okay, so make our line symbol here. So if that's the case, and then basically like the experiment you do is that you keep generate a number between 1 to 100, right? And you repeat that procedure maybe for 7 times, right? 7 times for the first prize. And maybe if you have more prizes, you can also do that for other prizes. But let us just focus on one prize. Okay, so you see what happened in here. So if the other case, and then the computer do is that it will generate a number 1 to 100, right? Uh, that's the experiment it does, and it keep doing that for 7 times, right? So basically, just a sequence of regenerating the number from 1 to 100 and repeat it for 7 times. And trial here, basically trial here just is just each time it run, right? So one time run is a trial, and the outcome here is just the number, right? So say the first time the computer is generate a number, and it maybe land to 1, maybe 99. So anything between a 1 and 100, right? And the second time it do it again, and it give you a number. The third time I do again, it give you a number. The fourth time, the fifth, the sixth, and the seventh time, right? So if you consider only one price, and for other price, the procedure will be repeated. Doctor at a research hospital are conducting a study to see if flu patients receive a flu vaccine in the past year. To collect the data, they asked people, a person treated for the flu at the hospital, whether they receive the vaccination, right? So in this case, what they do is that they just keep asking people, right, who treated right, for flu, right, if they receive vaccine or not, right? So the experiment here is just a sequence of people who ask, right, whether they get vaccine or not, right? And the people here is the people who treated for flu in the office, right? And the trial here is just the asking each person, right, you receive vaccine or not, right, in the past year. And the outcome here it will be yes or no, right? So people say either yes, I did receive the vaccine, or no, I didn't, right? So let us also look at the solution here. So the solution here, experiment computer generate, right? Trial 1 generated number, the number here, right? And the experiment here is asking flu patient, trial asking one patient, right? And outcome. For part A, actually we can make it clearer, okay? Clearer. So if there's something you feel confused, you're not sure, and just talk to me, okay? Identify the numbers in each of the following. Give the property as a reduced fraction, okay? Reduced fraction. So here they want fraction. So read it carefully, okay? Reduced fraction. There are 52 cards in a standard deck of cards, right? With 4 of each type of card. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, Queen, King, so just standard deck, right? Let event A be choosing seven out of a deck of cards, okay? So we care about if we get a card seven or not. So the first question, how many cards are in a sample space? So which in this case just 52, right? The standard deck. How many cards are in event A? So event A, because A, what A about is just a card number seven, right? So you can get a seven club, spade, diamond, and heart, right? So you have four. What is PA? The probability choose seven out of the deck of cards. So in this case, because in your sample space you have a 52, right? In A, you have four possibilities. So the probability will be 4 by 52. And if you reduce fraction, it become 1 over 13, right? 1 over 13. 64 first-year students have arrived at Hogwarts. They are divided equal in four houses, Hufflepuff, Slytherin, Ravenclaw, Gryffindor, and let age be the event that a student is assigned to Hufflepuff. How many events are in the sample space? How many? So in this case, the sample space is just let's say that a student is assigned to Hufflepuff. That a student is assigned to Hufflepuff. So basically, like in this case, how many elements in sample space? Okay. Oh, so in this case, like the sample space will be what we care about is 64 students, right? And then we divide them in different houses, and we consider the age in the event a student assigned to Hufflepuff, right? So in this case, the sample space we consider is all 64 student, right? Student, right? And how many elements are in the event age? Um, uh, at the time, you see that because they are divided equally, right? Equally to four houses, right? So basically, like when you assign people, and we have 64 people, and so which means each house you got 16, right? 64 by 4, you get 16. Um, what is pH? Probability of age. Probability a student be placed into Hufflepuff. So again, the sample space you got 64 students, um, and even age you got 16, right? So the probability would be just 16 out of 64. So maybe 1-4, right? 1-4. Um, but we can also understand it more intuitive in the sense that, because you had four houses, right? And you are randomly assigned. So basically, the probability you get assigned in Hufflepuff will be 1-4. Answer the following question. So let us also look at the solution, okay? I think we have it correct here. Correct, okay. Answer the following questions related to experimental probability. The probability that Rennie is on time for a given class is 29%. If there are 79 classes during the semester, what is the best estimate for number of time Rennie is on time to class? Round to the nearest integer. So again, I just keep saying, just keep 3, okay? So you don't have to think about that too much. So here, like, the probability she on time is 29%, right? Upon 9, right? So basically, like in this case, if you take like she have 79 classes, right? So the number of classes she on time will be just 79 times 29%, right? And if you do the math, it should give you about 22.91. If you round to the integer, this you need to calculate the number on time, right? So you have to make it to the nearest integer. Yeah. So in this case, it will be 23, right? 23. You flip a coin 20 times and get a 12 11 times. Uh, Based on this experiment, what experimental probability of flipping a coin getting a tails? So you get 11 tails out of 20, right? So the probability would be just 11 out of 20. And you do the math, it gives you about 0.55, right? 0.55. 55% if you want to use a percentage. Assuming it's a fair coin, what is the theoretical probability of flipping coin of getting a tail? So if you have in this case, it has nothing to do with the data you got, okay? Because they say assuming it's a fair coin, what theoretical probability, right? So here theoretical, which means if you have fair coin, right? But what probability you get a tail? So we have, right? Have a 50%, 0.5. Evaluate each probability, give answer as a reduced fraction. Ronald finished his daily jog and wants a drink. In his refrigerator, there are 2 cans of energy drink, 9 cans of soda, 11 bottles of water. So if he choose a drink at random, right, what probably he choose bottled water? So in this case, because he had like 11 bottle of water, right? And totally he get like 2 plus 9 plus 11, which is 22 kind of drinks, right? So if he just randomly choose, so the probably he get the water will be 11 out of 22, which he have. Here they ask for reduced fraction. Okay, so just put half here. There are total 38 possible equally likely outcome on a roulette wheel. Out of 38 outcomes, there are 18 odd number outcome. What probability of spinning odd number? So again, 18 out of 38, right? And you reduce it, give you 9 out of 19. A data analysis has best she's number 1, 2, and database is number 1 to 3, and presentation numbers 1, 2, 3, 4 to work on this week. If a single item is picked at random to work on, what probably item database is a database and has an odd number? So database and has an odd number, which in this case you got a 1, 3, right? Database number is 1, 2, 3, right? 1, 2, 3. And an odd number, right? Database and has an odd number, so you can get either 1 or 3, right? And among the items, you have how many items here? 2 items for the spreadsheets, right? 1, 2. 3 items for database, 1, 2, 3. And 4 items on the presentation, right? So which is 4. So 2 plus 3 plus 4, which is you got 9, right? So basically, if you pick a single item, it will be 2 to the 9, right? So you can think like, you have a spreadsheet number 1, spreadsheet number 2, database number 1, database number 2, database number 3, and presentation number 1, presentation number 2, presentation number 3, and presentation number 4. So get totally 9 items to work on, right? And we care about the event. You get database number 1 or database number 3, okay? So it will be 2 to the 9. Okay. Green Valley High School has an 11 math classroom, 8 science classroom, and 6 history classroom. And it's still the same, right? So each bigger classroom random. What is probably the classroom is for math or history? So here the OR event. The OR event is basically just check both either way, right? Either way, either math or history. So either math or history, you have like 11 math and 6 history. So you have 17. In a total classroom here, you get 11 plus 8 plus 6, which is 25, right? So the probability will be 17 out of 25, right? 17 out of 25. Students in Simon class, so coupon books last 4. 2 students sold 3 coupon books, 6 sold 2, 9 sold 1. If a single student is picked at random, what's the probability that students sold fewer than 3 coupon books? So how many students feel so less than 3 coupon books? We have like either, which means 1 or 2, right? So in this case, you have a 6 plus 9, which is you have 15 students who sold less than 3 coupon books, right? And the total student we have is 2 plus 6 plus 9, so it is 17. So in this case, it's just 15 out of 17, right? And the 15 is the number of students who sold less than 3 coupon books. A carnival game has a pool filled with ducks labeled from 1 to 40. If a child playing a game is allowed to pick one duck at random, what is the probability the child will choose a duck that is not multiple of 6? So here is the multiple of 6 from 1 to 60, right? So basically you need to check, like in this event, what the possibility symbol event can happen in this event, right? So multiple of 6, you have like 6, 12, 18, 24, 30, and 36. Okay, so here multiple between 1 and 40. So from that, you can see that you have like 6 is the size, right, of your multiple, right, um, of 6 event. So here the probability will be a child choose duck. Thus is not, oh, so here not multiple of 6, okay. So we need to be a little bit careful here. So if for multiple of 6, you have 6 cases, right? So the probability if you choose a duck is a multiple of 6 will be 6 out of 40, right? So here, because they ask you not a multiple of duck, of 6, I'm sorry. So which means just a complement, okay? So 1 subtract 6 out of 40, and you do the math, it should give you 34 by 40, and the reduced form is 17 by 20, okay? 17 by 20. If the probability of a randomly chosen college student is up to date on vaccine A 0.42, then what the probability that a randomly chosen college student is not up to date vaccine? So it's a complement, right? Again, so if the probability up to date vaccine is 0.42, so not up to date vaccine, just 1 subtract 0.42, which is 58, right? 58. This question a little bit not in the stream with asking for fraction, right? Give answer. So, but if you want reduce fraction 0.58, you have to translate to 58 by 100, right? And if you do a little bit further, right, it will be 29 by 50. But again, I mean, even you give the decimal, I think this also should be fine, okay? Because in any way, when we talk about probability, we should translate it to a number between 0 and 1, okay? So this is a universal agreement. And again, we also have the solution here if you want to look at the solution to compare, okay, with what we just discussed. I think like everything just the same, right? Like we discussed. So this is a little bit like abstract, right? Abstract. Yeah. Okay, so now determine independent, mutually exclusive event. Determine whether the following are mutually exclusive. So which means P, A, and B equal 0. A and B have nothing overlap, right? If you look at the Venn diagram. At certain school, intro to economics and intro to calculus meet at the same time. So it's impossible for students to take both classes. So if in this case, again, it is not so clear to me, okay? It can be rephrased in a better way. So basically, if you didn't know A, the event, the student can take the intro economics, and B, the event, the student can take the intro calculus, right? For this school, right? So other time, like A and B will be the mutually exclusive, right? Because they meet at the same time. So basically, like, it's impossible for the student to take both classes, right? Because you can see conflict time, so they won't be able to attend both classes, and also how can they do the test, right? Even A is rolling a 2 on a 6-side die, even B is rolling a prime number on a 6-side die. So the 2 is even A, but for B, the prime number is that you remember it can not be divided, right, anymore. Right? So basically, like it had only like itself, it can divide by itself, and it can divide by 1, right? So for when you roll a die, um, the prime number possible will be either 2 or 3 or 5, right? 2, 3, 5. So in this case, like we have an overlap here. And also, if you recall in your high school, right, 2 is the only even prime number, right? There are no other even prime number except for 2. So in this case, we don't have that mutually exclusive because we have something common here. Even A, drawing a heart from a deck of cards, and B, drawing a spade, right? So if you draw hearts, you for sure that card cannot be a spade, right? And vice versa. So C is mutually exclusive. So both A and C mutually exclusive, right? But not B. And here I determine whether the following events are independent, okay? Which means like one occurrence had nothing to do with the other. You roll a die and then you flip a coin. So for sure, it had nothing to do, right? They should be independent. You roll a die, then you roll again. Again, here, it should be independent. The first row should have nothing to do with the second row. You draw a card from a deck with a replacement, okay? Then you draw a second card. So in this case, thing will change, right? Because you draw without a replacement. So if you take a card out and you do a second draw, right? So the second draw for sure it will affect it, right? Because now you only have 51 card instead of 52. So these two will not independent, right? Or they will be dependent for C. So A, B independent, C dependent. Okay. You can also check the solution here. Yes, no, yes, right? Independent, not independent. Okay. Number 8, determine the probabilities and give properties at percent round to decimal place if needed. If a police officer pull over someone for speeding, okay, so if someone goes speeding, he either give the person the ticket or a warning, okay. So either way, they are mutually exclusive, right? Either property will give warning for speeding in 0.03, okay, and property that give either a warning or a ticket in 0.25, okay, in 0.52, I'm sorry. And what property a police officer will give ticket for speeding. Okay, so the wording is a little bit like confusing to me here. But if you read it carefully, basically like the ticket here, they have either category speeding or warning. Okay, and that property is 0.252. And because they are mutually exclusive, so that property also you can segment it by two small events, which is get a speeding uh, ticket plus get in a warning ticket, right? Warning ticket. So which means in this case, the warning ticket is 0.03. So which means the speeding ticket will be the remaining, right? Remaining. So which is 5.2 subtract 0.03, it will give us you will give us like 0.49. So let's check a solution here. Right. They're mutually exclusive. Ticket or warning is 0.52 and the warning is 0.03. And the ticket will be the remaining, right, which is 0.49. And if they ask for percent here to this, you just you make it 49%. Brian has two football games to play this week. If the probability his team lose the first game 0.2 and lose second game 0.5, they lose both game. What probability? So this case, basically like you can think, right? Uh, the two game result, right? Uh, has nothing to do with each other. So they kind of independent, right? Lose the first game and lose the second game. Um, and under this assumption, right? I think it's reasonable. And then basically like the probably losing both games will be probably lose first game plus time, right? Time. Probably lose second game. So which is 0.5 times 0.2, okay? So you got 0.1, 10% if you want percent. Um, for this kind of problem, I think, it would be better to stay a little bit clearer about assume that uh, the results for the two game independent, right? Independent. Suppose A and B are mutually event, exclusive event, right? Which is A and B have nothing to do with each other. And P B 0.24 and B A or B 0.27, find PA. So this case, it's just like a police officer example in problem in A, right? So PARB equal PA plus PB. And you already know PB, right? Which is 0.24, which is PA will be the remaining, which is 0.03, right? 0.03. And suppose A and B are independent event and PA 0.2, PA and B 0.12, and find PP. So this is again come back to the B problem, right? Well, losing two game, right? Problem. So PA and B for independent event, you can segment by PA times BB. So which means in this case, BB, you can find it by using 0.12 and divide by uh, 0.2, and it gives you about 0.6, 60% if you translate to the percentage. So then let's look at what we have here. Okay, lose game here, okay. A, okay, that's good. Number 9, okay. If probably of the student taking a yoga class 8.7, pilot class 8.6, both 8.51, what probably taking either yoga and pilot. So this is all event problem, right? If you didn't know, A is probably the event is the student take a yoga, B the event they take a pilots, and in this case, what you need to find is probably A or B, right? So we recall the formula for that, right? Uh, PA of B equal PA plus BB and subtract BA and B. So it will be 0.7 plus 0.6 subtract 0.51. And if you do the math, you should get a 0.79, okay, 79. The probability that an adult visit their dentist annual is 0.58. The probability that an adult has a mouth pain given they visit the dentist annually is 0.34. What the probability that an adult has mouth pain and visit their dentist annually? So this is just a multiplication rule, right? In probability, PA and B equal to BA times BB given A, okay? So in this case, if you didn't know A the event, the adult visit the dentist, right? And B the event, they get a mouth band, okay? So other time the B given A will be the event that he has a mouth pain, even he or she visit the dentist, right, annually. So from that, you can calculate P, A, and B, okay, by using the multiplication formula, just using 5A times 34 here. So let me just show you in solution here. So here A and B, right, will be has more band and visit the dentist annually. We G equal to PA times PPA. So PA is the event they visit the dentist, right? Annually. And PB given A here is just the event they get a mouth pain given visit, right? So you just plug in and that's give you the result you want here. You may have a bag containing 14 red marbles and 16 you have a bag containing 14 red marbles and 16 blue marbles. If you reach into a bag to draw two marbles at random, what is the probability you first draw red and draw blue without replacement? Okay, so which means in this case you don't put it back, right? So you carry when you draw the first red, right, and the second blue. So basically like it's a sequence event, right? Two event, A event you draw the red, and B the event you draw the second draw you get the blue, right? So that time again it would be A and B equal to BA. So this case just make maybe just use red and blue, right? We abuse the notation a little bit here. So probably a red and blue will equal to probably a red times probably a blue given red, okay? Blue given red, which means the second one you get blue, given the first time you get red, okay? So if we follow the strategy, so it just basically like probably we get a red at the first row will be 16 out of 30, right? You have 30 marbles. And probably a second blue, even the first red. So basically in this case, you see that it will be 16 out of 29, right? 29. Because you draw one red out and you didn't replace it back, right? So which means you have like 29 in total now. But because you did draw red, so which means like you have 13 red left and 16 blue left, right? So which means it will 16 out of 29. So your probability will be 14 divided by 30 times 16 divided by 29, okay? So this will be the answer, right? 16 divided by 29, 14 divided by 30, and it gives you this number. If A and B are even, that PA equal to zero point 0.7, PB equal to 0.2, and BA and B equal to 0.17, find PA or B. Uh, so this is a formula for the OR event, right? PA or B equal PA plus BB subtract BA and B. So you plug in, right? You get like 0.7 plus 0.2 subtract 0.17. It will give you 0.73. If A and B are then B and A equal 0.03 and PA 0.11, find PBA given property of B given A. So this is just the conditional property, right? It's another version of basically multiplication rule when you switch one term to the other side, right? So PB given A equal to BA and B and A divided by BA. So very straightforward. You just plug in, right? And it will be 0.03 divided by 0.11, and it give you about 0.273 if you keep 3 digits. Okay, so here, what you have here. Okay. Okay, now let's move on to the contingency table. We have the following incomplete contingency table show a random of 120 citizens, whether they have full-time part-time job, if they have children, right? Complete the table and answer the question below. Give property as a reduced fraction. So in this case, we have an incomplete table, right? Your job, you need to find it, to fill it, right? To fill it first, and before you can be able to, do anything. So, yeah, right. So in this case, you can see that we have doesn't have children. The total is 59, right? So for sure, this A will be in part-time A. So which means full-time you should it will be 51, right? In this case, you get 21 in part-time, right? And A do not have children, so you can also go here. So which means this case will be 13, right? And you can also fill up the total here to make your life, the calculation life eventually easier, right? You need one of those number in one of the below questions, okay? So after you fill up the table, okay? Which is 13 here, which is 51 here, and the sum you put here, right? 120 here, and this will be 13 plus 48, which is 61, right? Find birthday a citizen has a children and work full time. So citizen and has children work full time, which is this the cell we need to look at, like 48, right? 48. So 48 divided by the total, which is 120. Find the property a citizen has children or work full time. So citizen or work full time. So in this case, it's all even, right? Citizen, which is had children. I'm sorry, had children. So we belong the first row or work full time, which is the second column, right? So in this case, will be you can use the all event by uh, had children plus work full time and subtract had children work full time. Okay. So if you do that and you plug in, and let me just show you the math here. Children work full time, right? So children, so maybe we also just use this file, okay? So it will be easier for us to look at the number here because it already filled up here. So children plus full time, right? Subtract children full time. So children, in this case, you have like 61 out of 120. Work full time, you got 99, right? Out of 120, and subtract the common, which you just got from part A. And after that, you can get the reduced fraction here. Find probability that a citizen had children given they work full time. Okay, so given they work full time, which is you constrain yourself to this space, right? 99 here, and have children, which you got 48, right? So 48 out of 99. But here another track you can go by using the formula, right? Children given full-time probability children and full-time, which is 48 by 120, probability full-time, which is 99 by 120, so they both cancel out. But if you understand a bit clearer about the conditional probability, so which means at that time you only need to look at the full-time cell column, okay? So it will be 48 by 99 directly. So either way work, right? Either way. Find the probability that a citizen had children or does not have children. So in this case, like, people either have children or not have children, right? It's obvious, right? So it's just one, right? One. But you can also look at using the formula, right? Have children plus no children, right? And they mutually exclusive, right? So they, you can also do the math here, but I mean, if you think a little bit, right? And you should know that people should be classified either way, right? Have children, no have children, right? So which means it must be one. Find the probability that children does not have that citizen does not have a children, even they work part-time. So again here, you look at the work time part-time space, which is 21, and you care about does not have children, which is 8. Right? So 8 out of 21. But you can also use the formula here to work on that too. Find the probability that the citizen does not have children. So in this case, does not have children, you have 59, right? So 59 out of 120. Find the property that citizen does not work full time given they have children. So now given they have children here, which is you look at this row, right? And does not work full time, which means work part time, right? So you have 13 divided by 61, right? Find a property that a citizen work part time given they work full time. So given work full time, and find probably work part time, which is just completely nonsense here, right? Uh, so you look at the full time here, but you shouldn't be able to see any part time in this here, right? So it must be 0 here. But say if we do the math here, look at the formula way, part time given full time, part time and full time, right? So it won't happen, right? Either one, part time or full time with 0, right? So now we move to the probability distribution of discrete random variable, okay? Chapter 4. Determine whether or not distribution and probability distribution. Select reason why not. So to make it satisfy a probability distribution, we need three conditions, right? We have each value tied up with a probability. Probability must be 0 between 0 and 1, and the sum is 1, right? So the first chunk will be the given distribution of probability distribution sin probability lie inclusive between 0 and 1. Okay. The given distribution is not probability. So this is sin. Okay. So we look at this table, right? X equal 0, 1, 2. Each value type of probability. The sum its value between 0 and 1 is probably between 0 and 1, right? 0, 1, 3, 2, 3, right? And the sum is 1, right? 1. So it's a probability distribution table. So the second choice should not correct, right? Not a probability distribution, right? The fourth choice also not correct, right? So how about the the first and the third, right? The given distribution probability, since the probability lie, okay. Since the sum, okay. So each of them got a partially correct, right? Because it does not tell the whole definition, but I think this will be the choice. This will be the choice because nothing conflict here, right? Nothing conflict here. But again, in order to verify probability distribution is a valid one, you need to check three conditions, right? Each number, each outcome type probability between 0 and 1, and the sum is 1. Let's see. Okay, good. There are 60 musicians in the marching band. 12 band member is the percussion section, 51 in brass section, and the rest are in the woodwind section. X be the section randomly selected band member, complete the corresponding probability distribution table, and the value of fraction. So you have like basically I think it's like a screenshot 1, 2, 3 here. It's a bit making it a bit confusing, but anyway. So we have X a percussion here. So percussion here basically like how many you have 12, right? So 12 out of 16, 60, right? 12, 60. If you do the math, it gives you 0.2, I believe. And then for brass section, you have 25, right? 25 out of 60. So 25 out of 60, you can also plug in your calculator, okay, to get the number. Each one that is the decimal one. And then for the woodwind, you got like the rest, which mean 23, right? Woodwind. 60 subtract 12 subtract 25, you get 23. So if we woodwind will be 23 divided by 60, right? 23 divided by 60. So the px for the first part for percussion is 12 by 60. The second part will be 25 by 60, and the third one for woodwind will be 23 by 60. So let us look at here. Okay, correct. They are a player on a basketball team. They are practicing their free throws. By having each player shoot 2 free throws. The table below shows the results of each player free throw attempts, where N represents the missing, which is no, right? And Y represents the magnet, yes, right? Construct a probability distribution table made by the player, arranged increasing order, and Y probability simply fractions, right? So we have a player here. This person did 2 try, and he didn't make it. No. This person make yes, good. This person no, yes. One miss, one hit, right? This person hit, miss, yes, no, right? Yes, no, yes. So basically, if you didn't know X is the number of the free throws they make, right? So X can be 0, X can be 1, and X can be 2, right? Because they do 2 throw, right? So you can miss both, hit one, and hit both, right? So in this case, your X value will be 0, 1, 2, right? 0 corresponding to the case no, 1 corresponding to the case either yes, no, or no, yes, and 2 corresponding to the case yes. And from that, you can tally this table, right? No, which is 0, you get 1. So it will be the probability will be 1 out of 8. 1 out of the 8. And then hit one time, right? Either no, yes, or yes, no. You get here, and here. So you get 4, right? So 4 out of 8. 4 out of 8. And then for yes, right? You get this one, and this one. So we have 3 players make it. So we be 3 out of 8, right? So 1A, 4A, and 3A. So let's check. Okay. So here, right? 4A, 1 half, right? And half, right? 1, 2, which is half. 14. The table below show an incomplete probability density function for the description of variable x. The number of pets per house in a large neighborhood. What should be missing probability B? Provide final answer. So in this case, basically you should know that the summation will be 1, right? 1. So the missing is the one who make, not add up with one. So the probably people have four bets, right? We just one subtract the remaining chunk. So remaining chunk is 0.72, 0.02, 0.13, 0.11. So if you one subtract those, you should get a 0.02. So the missing piece here is 0.02, okay, 0.02. Okay, 0.02 here. Community festival sells 20,000 raffle ticket, $10 for each. There are four possible prize level. The grand prize golf cart value is $6,000. There are two winner of 1,000 and three winner of 500 and 10 winner at 100. Okay, so there let's see we have a sequence of this value here. What's the expected value of each raffle or raffle ticket? Okay. So value of a raffle ticket is that basically like um, how much you get back, right? So in that case, you buy a ticket, you didn't win. So the expected value is about negative 10, right? Negative 10, which is, you get nothing from that. I say if you win 100, so the expected here is 100 subtract 10, right? Which is 90. If you win 500, the expected value will be 490 because 500 take subtract 10, right? And the same thing for 1,000 and 6,000. And because when you buy a ticket, we don't know for sure you win or win, right? But from here, you can from the way they design the price, you can know what's the probability you get to such each scenario, right? So the probability you win $6,000 will be just 1 out of 20,000 because just one grand prize, right? For 1,000 winning, you get just 2 out of 20,000, right? For the win up price of $500, you only have 3 out of 20,000. And for the price of $100, you got the probability of 10 out of 20,000. So which means from that you can construct a probability table, right? With the expected value of the raffle ticket, where your X can take the value negative 10 with probability the remaining chunk of not winning, right? So in this case, you can see like 1 plus 2 plus 3 and plus 10 is 16, right? 16 winner, right? 16 winner. So the remaining 19,984 people will lose, right? Will lose the money. So the probability of you get negative $10 will be $19,984 out of 20,000. And the same thing, you can, your expected value of the ticket can be $90 and the probability tie with it will be 10 out of 20,000. The expected value of the ticket is 490 will be 3, right? 3 out of 20,000. The expected value of your ticket is 990 will be 2 out of 20,000. And the expected value of the ticket is 5,990 is 1 out of 20,000. So from that, you can calculate expected value by plugging sigma x times px, right? So just 5,990 times 1 out of 20,000 plus 990 times 2 out of 20,000 plus 490 times 3 out of 20,000 and plus plus 90 times 10 out 20,000 and plus negative 10 times 984,000 out of 20,000. So if you do this, right, like just this here, right, what I said here, you get negative 948. Okay. So the next chunk will be on average, player can expect again and lose, right? So of course they will lose, right? Because expected will be negative number, which is the amount 984 you just got 948, right? Dollar you just got from part A. A player can play a game by rolling a fair die several times. The player can win money based on number roll. The table shows probably each payout amount. Okay, what expected payout of the game? So you have payout here 100 for 800, for the 800, $180,000, and you have the corresponding probability. And so basically here, like they are missing, right? Because the remaining will be the payout will be zero, right? And with the property, whatever left, which is 1 subtract 0.17, subtract 0.029, subtract 0.002. So you should have you can construct a complete table here, right? Because here you just see the winning case. For sure, you have to pay some fee before, to play the game, right? But here we talk about payout, okay? So here, like you can see that you can also calculate expected payout, right? By using 100 times this, 4,800 times this, 180,000 times this, and plus 0 times the remaining probability, okay? So here you can see that, right? You can complete table. The remaining will be 0.8002. So which means uh, in this case you plug in, right? And you get this much, right? But the good news is that like actually even you don't need to complete the table, you still can do it correct here, right? Because 0 times anything is still 0, right? Time anything 0. But you put 0 here to make a complete picture about how your payout variable distributed, right? Distributed. And a lot of time people they just don't look at this, okay? They just look at how much they can make, okay? They don't really seriously look at this high chunk of probability. It's just a gamble mindset, right? The table presents the probability density function for the random variable x. Find the standard deviation of x around the final answers to two decimal places. So here, like in this case, you have a table or probability density function table here, and you want to find standard deviation. So you have here, you have just two columns, right? The first column is the value, and the second column is the probability. So this is a valid probability table. It has summing 1, right? It's probability between 0 and 1, each value type probability. So I would recommend again, just UTI, okay, for this kind of problem. Don't do a manual calculation because a lot of time it will cause you trouble, okay, given the time constraint. So let me just quickly UTI, okay, here, so you can see how we're going to process this with TI, okay. So you edit here, start edit, and you put in your list the L1, E3 here, 4, 8, right? And L2 is 1, 5, 2, 5, and 2, 5. Okay. So after you put the list here, you just do start here, calculate, One we will start here. Here one in list. Here two here. Okay. So this is your standard deviation, right? 2.154. 1.4. And if you want the variance, yeah, you can square. But here they ask for standard deviation, right? So let's look at the answer. So here in this answer, they use the direct calculation. I mean, it's fine with that, right? It helps you to understand the formula. But again, given the constraint time in your test, right, I would recommend just go with this TI track. Okay, it's faster and safer. In a large population, about 65% of people prefer chocolate ice cream over vanilla. A researcher takes a random sample of 12 people and survey whether they prefer chocolate or over vanilla ice cream. Use a binomial distribution to compute the probability that exactly three people, okay, in the same brief sample prefer chocolate over vanilla. Identify information required here. So here in this case, you have the percentage people prefer chocolate over vanilla, right? It's 65%, and you sample 12 people. So in this case, you have a sequence of 12 trials, right? 12 trials. So it just got a Bernoulli binomial, right? Trial, right? People independent, success or failure, right? Prefer, not prefer, and fixed probability 0.65, right? So trials here will be 12. The success number success here, like, um, yeah, because you care about exactly three people in a sample prefer chocolate over vanilla. So in this case, your X you care about is like three, right? Three. So if you consider maybe exactly four, so your X will be four, but for this given problem, right, we want three, right? We care about three. And the success probably 0.65, okay, 0.65. 54.4% of tickets sold to a movie are sold with popcorn coupon, and 45.6% are not, okay. You want to calculate probability selling exactly 6 tickets with popcorn coupon or 10 ticket, right? What should you use for parameter P? So what the event we care about here is we care about ticket with coupon, right? Ticket coupon. So in this case, the success here is the ticket sale with coupon, popcorn coupons. So in this case, 54% ticket, right? Sale with popcorn coupon. So this is the thing you care, right? The parameter you want to use, because this is the success based on the event you care about, right? We care about popcorn coupon, ticket with popcorn coupon. So the P will be 0.544 here, 54.4%. A soda bottling company's manufacturing process is calibrated so that 2% of bottles are filled within specification. Every hour, 12 random bottles are taken from the assembly line and tested. If three or more bottles in the sample are not within specification, the assembly line is shut down for recalibration. What property that assembly line will be shut down for recalibration? So in this case, basically like what we do with that, we will do random test, right? You random test like 12 bottle, right? 12 bottle. And the event we care about is that like if the bottle not meet the specification, right? Not within specification. And you shut down the line if you have three or more, right? So if you denote X is the number of random bottle among 12 bottle not within specification, okay? Another time you can model X by a binomial of 12, and the success probability is given here, right? So this machine, it has the 2% of the bottle not filled within specification, okay? So here again, success here doesn't mean good or bad, right? It just mean like the event we care. And people here, they care about that, the the bottle not within specification. So in this case, your X can be modeled by a binom of 12 and 0.02. And you want to calculate probably X greater than 3, which is the case you have to shut down the machine, right? So if you do that, basically you can see here, uh, X greater than equal 3, and your X follow binom of N12 and P 0.02. So here you can go with a track which is from 3 and above, which means either 3 or 4 or 5 up to 12, and you calculate its probability and you add up, right? But we would not recommend go with that track. Other we have to, we should to go another way around, which is use a complement strategy. So at least 3, right? From 3 and above, which is 1 subtract less than 3, okay? And less than 3, in your TI, right? It cannot process this directly. You need to rework on this a little bit, which is, because your TI with the binom CDF function, cumulative distribution, okay? It does not work with the less than sign, okay? I emphasize again here. Your binom CDF, it does not work with the less than sign. You have to translate a little bit, okay? Which is like less than 3, which means like 2 and below, right? 2 and below. So which means like probably X less than equal to. Another time, the binom CDF will work, okay? Will work. So you have to be very careful here, because a lot of time I see students just plug in binom CDF at 12.02 and 3 here, and it gives you a wrong answer, okay? It had to go down because the binom CDF, it work with the equal sign only, okay? And for this, chapter, we work with discrete distribution now. So the equal sign will be a serious thing, okay? So when you go to the chapter 5, 6, 7, when we have continuous distribution, and then you don't have to worry about the equal sign. But as long you work with discrete data, you have to worry about the equal sign, okay? So with that, you just plug in 1 subtract binom CDF here, 12.022, and it should give you the answer. So let me show you how you do that, right? With your TI calculator. 1 subtract binom of 12.02 and 2, right? So do start here. I think do second distribution here. Let's go from beginning here, clear here. 1 subtract, right? Second distribution here. Binom CDF here. Okay, binom CDF, which is up to, right? Triangle, you have 12. P, which is success here, which is you get can not miss standard, right? And the value here is 2, okay? 2. So which is 1 subtract by num. So it gives you 0.0015, right? So if you keep 3, will be 0.002, okay? A state lottery sell instant lottery scratch tickets. 11% of the ticket have prizes. Now goes to the store and buy 10. Okay, what probably exactly 2 tickets have prize? So in this case, you have a sequence event, right? When you buy 10 tickets, right? Which is just 10 random trials. They have nothing to do with each other, right? Each trial either success, win or not win. And the probability will be, success will be 11 out of, but 11%, right? Which is 0.11. So if you know X is a number of tickets have the price, you buy among 10 tickets, right? At that time, your X view can be modeled by a binomial of 10.11. Okay, 0.11. So this is the first step you have to do. And then now from that, you can do all the math here. What probably exactly two tickets have the price? So this case, it's just binom PDF, right? Exactly, which is equal, right? Binom PDF 10.11 and 2, right? Binom PDF 10.11, 2. Okay. So let us just use this file, okay? So we can save some time here. And again, you can also do that, right, with your calculator by doing second distribution by number PDF, right? 10, which is a trial, you buy 10 tickets. P is success probability. And you want exactly two tickets get the price, right? Is that 2? Yeah, 2, right? You enter here 0.214, 4. What probably all tickets have price, right? Which is probably x equal 10, which means if you do the math, it's pretty almost 0, right? What are the probability more than half ticket, more than half, which is greater than 5, right? And again, this way, you also do the track here. 1 subtract less than equal 5, right? So a complement greater than 5 is less than equal 5. So this case, we're lucky, right? Because you have an equal sign right away here. It's not like the previous case here, right? So just by num CDF 10.11, 5, okay? So you see, you have to be very careful attention here, okay? Don't be over smart here, and say less than equal 5 and you move one more step which is less than equal 4 and it make the wrong calculation, okay? I see some students, they kind of overlook this and they think less than sign and they move one more step and make it wrong, okay? So be very careful here, okay? So this is already give to us the binom CDF. What probably fewer than 2 ticket we have price, right? Fewer than 2, which mean less than 2, which mean 1 and below, right? And here again, you do binom CDF, you get that probability. What's the probability that at most half ticket, at most half, which is no more than 5, right? Which is less than equal 5, which is you already got it here. 0.997, right? 3, right? Are you even, you don't need to calculate this track, you just do a complement, right? More than half, add more half is a complement. So just 1 subtract here, you get this E here, right? The complement part C. What about the at least 2 ticket have price? At least 2. So which means greater equal than 2. And again here, you do complement 1, x less than 2, right? And which is 1 and below. And it gives you this number, okay? So again, for the binomial distribution, be special, make special attention on the binom PDF, which needs you to do the exact value, binomial probability density function, and binom CDF, it gives you the cumulative, right? Binomial cumulative distribution function. And it works only with the less than equal sign, okay? So if you have a less than sign, you have to go down a little bit to make it 1 unit, right? To make it less than equal, right? So this also concludes the review for Unit 2 here. If you have any question, then feel free to stop by my office hours, okay? We have a hybrid review for the Unit 2 test. And we can also use a Zoom link provided in the previous email. Thank you so much for your attention.